The homopolar or N machine is a very interesting device which was the brainchild of Michael Faraday in 1831. It has an intriguing method of operation and a remarkably large output. The principle of operation is incredibly simple. A copper disc is rotated in a magnetic field. Then power is developed between the shaft of the copper disc and the outer edge of that same disc. It also works if the contact is not on the outer edge but is in any intermediate position towards the edge. It was then found that the device will still operate even if the magnet is attached to the copper disc and rotates with it. Now that's something which is not intuitively obvious. The power output is tremendous, with the capacity of extracting 1,000 amps, but at a low voltage of less than 1 volt. The power takeoff can be from one face of the disc near the shaft, rather than having to have a copper shaft integral with the copper disc. This device also works with a magnet just attached to the copper disc and rotating with it. This looks like a very viable starting point to develop a device which can run itself and provide useful additional output, since a motor to rotate the disc will not require anything remotely like 1,000 amps to drive it. The snag is that it's very difficult to provide reliable sliding contacts capable of handling large currents for extended periods of time. This picture shows the disc with its outer edge immersed in a bath of mercury. This is sufficient for a brief demonstration at low power, but it's not realistic for a serious working device. It might just be possible to create a reasonable working device by accepting that the current output is not going to be anything like as large as 1,000 amps. Long life brushes could be made from solid copper bar and spring loaded against the copper disc in matching pairs so that the brush thrusts oppose each other and do not generate a sideways load. These could be made in multiple sets for each disc, say 4 or 8 pairs per disc, so that the effective electrical resistance between the brushes and the disc is reduced and the possible current draw increased. You see in the diagram here where there are 4 separate pieces of springy metal pressing against the face of the disc, both at the edge and near the center. Multiple discs could be mounted on a non-conducting magnetic shaft, and their brushes wired in series, and that would allow you to raise the output voltage. It's said that in India, Professor Tiwari used homopolar generators to extract hydrogen from water, and that bus services there were run on hydrogen as a fuel, but I've not managed to find any confirmation of that. The main difficulty in using the design is the difficulty in drawing off the very high current, low voltage produced without creating major drag factors, which is a serious problem. Bruce De Palma managed to overcome this problem, but he assigned his development to the US military. In 1987, 3 of the Borderlands science team, Michael Noe, Peter Lindemann and Chris Carson, experimented with the homopolar design and found that a much more satisfactory version could be produced. Their version produces sawtooth AC instead of DC, and so the output could be fed directly into a step-up transformer. Their design has 4 ferrite magnets glued between 2 metal discs, and for additional mechanical strength, copper wire was wound around the outer edges of the magnets in order to prevent magnets flying outwards if the glue bond should fail. So you have the 4 magnets, 2 south pole facing upwards, 2 north pole facing upwards. They're connected between 2 metal, typically copper discs, and then wires round them to make sure that they don't break free. They're mounted on a motor which spins the disc itself. The interesting thing is the output is being taken from 2 positions on the outer edge of the disc. This appears to contradict the laws, so-called, of conventional electricity, as there is a very low resistance short circuit directly across the brushes which pick up the AC voltage output. The output current from a small prototype was estimated at 100 amps. The frequency of the AC is directly proportional to the shaft speed of the motor, but the output voltage was almost independent of the shaft speed, increasing only very slightly with much greater speed. It was also found that putting the brushes at 90 degrees apart on the metal shaft of the motor gave the same output in spite of the contacts nearly touching each other. This design appears to have considerable potential for construction at a larger size and with further investigation. While the operation of these devices looks impossible at first glance, it needs to be understood that copper has some very unusual characteristics when interacting with magnetic fields. This is explained in the website www.resonantfractals.org, which says, "In electronics, we're often given information that is not true. This is the most important one to me, as what we were told hides a quality of copper. When we bring a magnet up to a spinning copper cylinder, it is pushed away and does not want to touch the cylinder. Once released, the magnet shoots across the room at high velocity. Some have conjectured that this force that pushes the magnet away is a reversed magnetic field emitting from the copper cylinder in motion across its magnetic field. They say this is a quality of magnetism or electromagnetism. So we set up this experiment to use a compass inside the spinning copper cylinder to measure this reversed magnetic field which we expected to see, and we discovered that it does not exist. The force pushing the magnet away from the spinning copper cylinder does not affect the magnet's field or the polarity of that field, as when we bring 2 magnets together in opposition or 2 like poles. They repel. There is no north-south reversal of the magnet's field at all as it extends through the spinning copper. It does not even matter how we orientate the magnet. The force is much stronger than 2 opposing magnets can become. Seeking the answer to what this force is takes us into the level of the proton and the mass in motion of the copper medium. Copper is not magnetic, it is electric, and from this experiment we discern that it also has some interesting inertial coupling qualities. The force of the spinning mass of the copper is transferred into the magnet's mass. The 2 forces we can detect when we release the magnet, one is propulsion across the room at high velocity, and one is repulsion at 90 degrees to the repulsion, keeping the magnet from touching the spinning copper. This shows us likely why the electrons in an atom do not crash into the nuclear center, where the protons and neutrons are located, inside the strong force field bubble. Further, when we spin up a steel cylinder, and note when a magnet is brought up to it, there is only one field force noted. The steel is magnetic, and yet it does not push the magnet away or try to shoot it off at 90 degrees. It simply pulls straight at the steel which is rotating, no matter how fast we make the steel cylinder spin. And one might realize why, therefore, magnetic bearings are frictionless. There's no inertial mass coupling between them. Nikola Tesla took Faraday's 1831 design further, as can be seen from his 1889 US patent number 406968. He remarked that to get any kind of useful power from the device would require a copper disc of very large diameter, or a disc which is spun very fast. A large copper disc would be an inconvenient size, and a high rate of rotation makes it very difficult to get a good long-lasting sliding contact at the outside edge of the disc. He also pointed out that current flows from the shaft out to the outside edge if the magnetic field passing through the disc was in one direction, but if the direction of the magnetic field were reversed, then the current flow would be from the outer edge inwards to the shaft. The same change of direction of the current flow also happens if the direction of rotation of the disc is reversed. Using those facts and considerable ingenuity, Tesla proposed an arrangement where the power takeoff is from the axle alone. By using two copper discs and magnetic fields which moved in opposite directions. This arrangement has the advantage that it has an output voltage which is the sum of the two separate voltages. This basic concept uses 4 ring-shaped magnets and 2 discs of copper, brass or iron. Both of the discs are given a wide flange as shown here. The flange is at the outer end of the central disc. There is a gap between the two flanges, that is between the two discs, even though it's being used in conjunction with each other, and the load is connected, interestingly, between the tip of the rotating shaft rather than having it on the side of the rotating shaft. The load is powered between the two. The gap breaks the connection between the discs, and Tesla dealt with that by using a flexible metal belt linking the two discs together. That's the belt running outside the two discs themselves. While it's possible to use the belt to drive one of the discs, Tesla did not use that method. The belt overcomes the need for a sliding contact at the outside edge of the discs, and so both sliding contacts are at the axles, which is an easy place to have a sliding contact. Tesla shows the contact against the end of the axles, as that's just a rotary movement with respect to the stationary contact. But even if the contact pressed against the outer face of the axle, the sliding movement would still be relatively slow. In spite of this clever design from Tesla, I've never heard of anybody building this style of generator in spite of the large output currents which it can generate.